Hello everyone, I hope you're doing great, and in this video I want to welcome you to a new series of videos that I'm going to be doing where I'm gonna cover some basic electronic information that is not widely available on YouTube videos. I'm gonna try to keep these videos pretty small and dense so you can get as much information as you can in a small amount of time. So before we get into this video that is gonna cover the topic of voltage doubler, I want to let you guys know that if you like this kind of videos, electronic videos, and you want me to continue this kind of videos, please give me a like and subscribe to the channel for more videos, but also leave a comment down below if you liked it, and maybe leave a comment about any mistakes that I did so I correct myself. So let's get into the video. So a few days ago I salvaged a transformer from an old UPS that I had laying around, and I was thinking about using this transformer to power my audio projects and or my amplifier projects. But there was I had one problem with the this transformer, and this transformer didn't have a center tap. And I was thinking and trying to search for ways in order to have a dual supply powered from this transformer. And I encountered the circuit of a voltage doubler that actually you can use this voltage to produce two DC voltage rails without using the center tap. So in this video we're gonna cover some of the problems of the single to dual supply rails, which are the problems of using a single supply to power dual supply circuits. We're gonna cover the circuit of the voltage doubler. We're gonna show some simulation of a full bridge rectified AC signal, full bridge rectifier signal with center tap, and then check the voltage doubler. We're gonna show the voltage doubler in action to a breadboard I have here, and also we're gonna suggest at the end some improvements that we can do to our final supply. So if you think of the problems of the dual supplies, that the dual supply circuits that are powered from single supplies, think that if you have an op-amp or power amplifier, you have to bias the input into half of the voltage of the DC supply. And this biasing actually requires additional components like resistors to bias into half the supply, but also you need filtering caps at the input and at the outputs, so you block the DC supply going into your signal input, but also the DC supply from your final signal output. These are the problems when you try to bias your circuits at half the voltage. The next thing you can do is that you can still use a full bridge rectifier at your transformer without a center tap, but then in this circuit you still need to use half of the DC rails, and you have to use again coupling caps and additional components. The other thing that you can do in order to split your rails of the full rectified DC output of your power supply that you use your transformer is to use regulators that use feedback to hold the voltage of the common supply into a stable voltage, and you have a stable reference from the higher and the lowest point. And still in this application you still need to use regulators. You have to use additional components for the regulators. So you can minimize this problem by if you have a center tap to your transformer, but you still have to use half of the rails of your DC signal. So if we do the simulation here, in this circuit and the first circuit, we've got you can actually model your transformer as an AC output that has a certain peak, and this is the circuit of the full bridge rectifier. And if we check at one side, we see that we use all the peak. We use the peak of the half wave, and we also use the peak of the other half wave of the sine wave. So if we check the next circuit that uses a full rectified signal AC source, but also has a center tap, you can actually model transformer with a center tap as two AC signals that have a common point, and you reference every point of your circuit in this common point. And still, if you check here, you still use full rectified signal, but you use half the signal because this is all the circuits of all the components of your circuit are referenced to this common point that it is the center tap. So for each DC rail, you use half the supply of the given supply of the transformer. So some of the pros of the full rectified signals, the full bridge rectifier signals, is that for a given load, you can use smaller capacitance values to smooth the rails and create a DC supply. So because here, as you see, you use both the positive half wave and the negative half wave, which is actually rectified. So you can use both of the positive and the negative supply. So if we go to the voltage doubler here, you see that we use two diodes to this point in order for the first half wave. We see that the current flows from this diode across this resistor and goes back into the transformer from this point. And as you see here, no current at this state at the half wave is passing through this resistor, because at this point you've got higher voltage, so you don't have any current. So this, on the first half wave, you see current flowing from this side across this common point and back into the transformer. On the negative half wave, we've got current flowing from that point here in the common point. It doesn't go here because this diode is reverse biased, and you've got current flowing through this resistor down there and into this diode back up there and returning back to the transformer. And as you see here, we use one half wave and full peak. As you see here, we've got 20 peak voltage, and we use full the first peak for the one part of our circuit, and we use the negative peak to supply the other part of our circuit. And these two supplies are actually independent one to the other, because as I explained earlier, when one diode is working, the other is not working, it's reverse biased, and we don't have any current flowing from this when this is working, or this when this is working. So this has some pros, as you saw from that simulation, that we can use the whole positive peak for the supply of one rail and whole negative peak for the supply of the other rail by using this common point here. Some cons of this circuit, the voltage doubler, is that you need twice as big capacitors to smooth out this wave, because as you see here, these peaks are actually you have these peaks in a longer times if you compare it to the other peaks, and so you need bigger capacitors to supply with current your load for bigger times, because you don't have this peak that you have in the full rectified signal. So that is one con of this circuit. So you need to use twice as big capacitors in respect with the full bridge rectifier circuit for a given load. We did some of that simulations, and we explained some of the differences between those circuits, and now we're gonna show the voltage doubler on our breadboard. So here we have the voltage doubler circuit on the breadboard. I've got my transformer hooked up at the plug. This transformer has a peak of 20 volts, and as you see here, I've got the two cables connected into my breadboard, the voltage input into my breadboard, and as you see, I'm not using the center tap. I also have these two diodes that we're using also at the simulation, and I've got two load resistors of 1K resistance. I also have the upper point of my one resistor hooked up to the probe of the oscilloscope to channel 1, and I've got the probe of the oscilloscope of channel 2 into the negative, the bottom point of the second resistor, and I also have my ground connection into the common point of these two resistors, which are also the point that goes to the transformer. So the two diodes and the two resistors, and if we check the oscilloscope, we see that we have created two different voltages. We've got one voltage for the one resistance, the one resistor, and one voltage for the other resistor. And as you see, practically when one resistor is supplied with voltage, the other one has 0 voltage and is actually completely independent of the currents, and maybe some voltage is created around the other resistor, or maybe a circuit that you are supplying. And as you see at the second supply, when we've got voltage here, we've got minus the peak of this voltage here. We don't have any voltage on the other resistor, and the other resistor is completely independent of the working conditions of the second resistors. And as you see here, if we hook up a capacitor across the upper point of the resistor and the common point, a capacitor, we see that we have smoothened the signal of the second resistor, and it's not like the first like this one on the first one, and we've got almost stable DC voltage. And as you see here, we've got some jumps because of the load when the resistor is supplied with voltage. When the resistor is supplied with voltage. So this is the video. I hope that helped you to understand some of the points of the voltage doubler, and in the next video we might talk about some of the improvements that you can do to this circuit. You can use regulators to regulate the power and actually create a more stable DC voltage. So if you like the video, give me a like, subscribe to the channel, and also leave me a comment of any questions that you have remaining. And till next time, good luck, and I will catch you later. Bye.